Hello and welcome to the session. Principles of Computer Systems, LO4, understand the fundamentals of logic circuits and gates. How do computers perform complex calculations and make decisions? The answer lies in the fundamentals of logic circuits and gates. Dive into the world of binary logic and discover how these components form the backbone of digital systems. Logic circuits are essential to digital computer systems. They use binary logic, where signals are either 0 or 1. By combining logic gates, computers perform calculations and control hardware. These gates follow Boolean logic rules to produce specific outputs. Understanding these basics is crucial for digital circuit design. Logic gates like AND, OR, and NOT are fundamental. The AND gate outputs 1 only if all inputs are 1. OR gate outputs 1 if at least one input is 1. NOT gate inverts the input value. These gates are building blocks for complex operations. NAND and NOR gates are functionally complete. NAND is the inverse of AND, and NOR is the inverse of OR. NOR outputs 1 when inputs differ, while NOR outputs 1 when inputs are the same. These gates are crucial for arithmetic circuits. They allow for diverse logical operations. Logic circuits are integral to arithmetic units, memory cells, and control units. The ALU in a CPU is built from these circuits. State machines use sequential logic circuits for control. They combine gates with storage elements. This forms the core of digital system functionality. Correct. Good logic design enhances performance and reliability. It reduces power consumption and delays. Poorly designed logic can cause inefficiency and unpredictability. Logic gates and circuits are essential for executing software instructions. They enable controlled and reliable digital system operations. Computer systems use binary to represent information. Binary aligns with electronic hardware operations. It forms the foundation of data storage and processing. Binary uses two values, 0 and 1. This simplicity makes it ideal for digital systems. Binary uses base 2, consisting of 0 and 1. Decimal uses base 10, intuitive for humans but complex for hardware. Hexadecimal uses base 16, simplifying binary data. Each hex digit corresponds to 4 binary bits. It aids in programming and debugging. Binary offers simplicity and reliability for hardware. Decimal is user-friendly for human interaction. Hexadecimal balances readability and machine relevance. It shortens binary sequences for easier management. These systems serve different roles in computing. Binary values match physical electrical states. 1 represents high voltage and 0 represents low voltage. Transistors act as electronic switches in logic gates. Memory stores bits as electrical charges or magnetic states. This ensures consistent data processing. Logical operations are based on propositional logic. Statements evaluate to true or false, represented by 1 or 0. Logic gates perform these operations on binary inputs. They translate logical reasoning into electronic behavior. This forms the basis of digital systems. Truth tables define logic gate behavior. They list all input combinations and corresponding outputs. Designers use them to verify logic before implementation. Truth tables ensure correct electronic behavior. They are fundamental for designing digital circuits. Transistors implement logical operations in circuits. They act as switches, controlling electrical flow. CMOS technology combines NMOS and PMOS transistors. This ensures reliable logical outputs with low power. Transistors are the physical basis for logic gates. And OR gates are built from transistors. Series connections implement AND behavior. Parallel connections implement OR behavior. NAND and NOR are fundamental in CMOS design. They are building blocks for all logical operations. XOR gates output true when inputs differ. They require complex transistor arrangements. XOR uses combinations of NAND, NOR, and NOT gates. XNOR inverts the XOR output. These gates are vital for arithmetic circuits. Arithmetic relies on structured logic circuits. The half adder adds two binary digits. It uses an XOR for sum and an AND for carry. Full adders extend this for multi-bit addition. These form the core of the ALU in CPUs. Transistors control current flow, acting as switches. Early computers used vacuum tubes. The bipolar junction transistor revolutionized design. Modern systems use MOSFETs for efficiency. They represent binary values through conductivity. HDLs like Verilog design logic circuits at hardware level. Designers describe logic behavior, not transistor wiring. HDL code synthesizes into hardware implementations. This allows simulation and testing before fabrication. Verilog enhances reliability and performance. Transistors act as switches representing binary states. Logic gates perform basic logical decisions. Arithmetic circuits enable binary addition and carry handling. ALU operations execute program-level calculations. HDLs describe and implement logic in hardware. Complex arithmetic builds on transistor-based logic gates. Layers of abstraction allow for reliable operations. Logic gates form arithmetic circuits for processing. HDLs optimize these designs for performance. This structure supports modern computing capabilities. In conclusion, understanding the fundamentals of logic circuits and gates is essential for explaining how computer systems process information. Logic gates such as AND, OR, and NOT form the building blocks of digital circuits, enabling binary operations and decision-making. These circuits underpin the operation of processors and digital systems. Understanding logic circuits and gates provides a foundation for system design, troubleshooting, and further study in computing and electronics. Thank you for watching this video. If you have any questions, please feel free to contact us via email or WhatsApp at 07484361688.